Welcome to this tutorial on sketching signals from given equations. Today, we'll learn how to sketch the signal given by the equation x of t equals u of t plus 1 minus 2 times u of t plus u of t minus 1. Step functions like these are fundamental in signal processing and systems theory. First, let's understand what the unit step function u of t means. The unit step function, denoted by u of t, is defined as u of t equals 0 for t less than 0, and u of t equals 1 for t greater than or equal to 0. Graphically, it looks like this. It's 0 for all negative values of t, and then jumps to 1 at t equals 0, and stays at 1 for all positive values of t. Now, let's understand the shifted versions of the unit step function in our equation. First, we have u of t plus 1. This is the unit step function, shifted 1 unit to the left. So u of t plus 1 equals 0 for t less than negative 1, and 1 for t greater than or equal to negative 1. Next, we have u of t, which is our standard unit step function. Finally, we have u of t minus 1. This is the unit step function, shifted 1 unit to the right. So u of t minus 1 equals 0 for t less than 1, and 1 for t greater than or equal to 1. Let's visualize all three step functions on the same graph to better understand their relationship. The blue line represents u of t plus 1, which steps up at t equals negative 1. The green line represents u of t, which steps up at t equals 0. The red line represents u of t minus 1, which steps up at t equals 1. Notice how they're the same function, just shifted along the t-axis. Now, let's calculate x of t using our equation x of t equals u of t plus 1 minus 2 times u of t plus u of t minus 1. We need to evaluate this expression for different regions of t. Let's divide the t-axis into 4 regions. Region 1, t less than negative 1. Region 2, t between negative 1 and 0. Region 3, t between 0 and 1. Region 4, t greater than or equal to 1. Let's calculate x of t for each region. For region 1, where t is less than negative 1, u of t plus 1 equals 0 because t plus 1 is still negative. U of t equals 0 because t is negative. U of t minus 1 equals 0 because t minus 1 is negative. So x of t equals 0 minus 2 times 0 plus 0, which equals 0. For region 2, where t is between negative 1 and 0, u of t plus 1 equals 1 because t plus 1 is positive or 0. U of t equals 0 because t is still negative. U of t minus 1 equals 0 because t minus 1 is negative. So x of t equals 1 minus 2 times 0 plus 0, which equals 1. For region 3, where t is between 0 and 1, u of t plus 1 equals 1 because t plus 1 is positive. U of t equals 1 because t is positive or 0. U of t minus 1 equals 0 because t minus 1 is still negative. So x of t equals 1 minus 2 times 1 plus 0, which equals 1 minus 2, which equals negative 1. For region 4, where t is greater than or equal to 1, u of t plus 1 equals 1 because t plus 1 is positive. U of t equals 1 because t is positive. U of t minus 1 equals 1 because t minus 1 is positive or 0. So x of t equals 1 minus 2 times 1 plus 1, which equals 1 minus 2 plus 1, which equals 0. Let's summarize our findings with the piecewise definition of x of t. X of t equals 0 for t less than negative 1. X of t equals 1 for t between negative 1 and 0. X of t equals negative 1 for t between 0 and 1. And x of t equals 0 for t greater than or equal to 1. Now, let's plot the final signal x of t. From negative infinity to negative 1, the signal is 0. At t equals negative 1, the signal jumps up to 1. It stays at 1 until t equals 0, where it jumps down to negative 1. It stays at negative 1 until t equals 1, where it jumps up to 0. From t equals 1 to positive infinity, the signal is 0. This is what we call a pulse signal, specifically a rectangular pulse with different amplitudes. It has finite duration and is 0 outside a finite interval. In conclusion, we've learned how to sketch a signal from an equation that involves step functions. The process involves 1. Understanding the behavior of each step function in the equation. 2. Dividing the t-axis into regions based on the transition points of the step functions. 3. Evaluating the equation in each region. 4. Drawing the resulting piecewise function. This technique is essential in signal processing and systems analysis, where step functions are commonly used to model real-world signals and systems. Thank you for watching.